So thank you for the introduction and welcome to this acoustic webinar about simulation of acoustic transmission. So let's get to the agenda of today. So this webinar will include first an introduction to the topic of acoustic transmission and insulation. And then we will see design objectives that vary depending on the types of products. For some products, we would like to increase the transmission while reducing the insulation, while for many other products, we would like to reduce transmission and increase the insulation. And we will review an indicator for describing acoustic transmission, which is called the sound transmission loss. Then we will walk through a modeling process in Actran to simulate the sound transmission of building partition. So I will demo lively the modeling of the structure, applying the random excitation of diffuse sound field on one part of the partition and get the transmission on the other side of the partition to calculate the sound transmission loss. And then we will review several other case studies on the topic of acoustic transmission. So they include transmission through a car window with the effect of the thickness evaluated. And a second case on the effect of the ceiling design on the transmission of a car window as well. And the last case is a wind noise transmission into a simplified car cabin. And finally, this webinar will end with the Q&A session. So let's get started on the topic of insulation and transmission. So acoustic transmission is a frequently encountered topic in several industries like automotive, aerospace, construction, shipbuilding, and consumer goods. So depending on the type of products that we design, the objective can be different. For example, for many cases in automotive, in aerospace, and in construction, objective is to increase the insulation while reducing the transmission. And in other cases, especially for the casing design of electronic devices, we would like to, on the other hand, increase the transmission so that the acoustic signals emitted by a speaker or received by a microphone can go through easily the casing design. Now, take a standard example of sound transmission testing for automotive industry or for construction industry. Now, in testing, we often have these types of setups. So here on the left, we see in testing a reverberant acoustic room next to an anechoic room, and the tested object is placed in between of both rooms. So this is typically set up for testing the transmission of automotive panels. And in construction, sometimes we have the case where two reverberant rooms are placed one next to the other one with the tested panel placed in between of them. So in both cases, on the left room, there will be a intense acoustic excitation injected through the speakers, and due to the reflection of the rigid wall, a diffuse sound field will be formed and be applied on the object, and which will induce vibration of the object, which consequently transmit acoustic waves on the to the other side of the room. And a key indicator to characterize the transmission capabilities of that object being tested is the transmission loss indicator. There are several definitions about transmission loss. One that I put here is the uses the ratio of the incident acoustic power on the left and the transmitted acoustic power on the right. So the logarithmic scale of that ratio gives the transmission loss, or TL in short. Of course, there are other indicators like the transmission coefficient in construction, the sound transmission class, noise reduction, or insertion loss, etc. So during this presentation, I will concentrate on the simulation of the transmission loss of a complex panel in Actran. So Actran is the acoustic software among the MSC software families. And then today, Actran has extensive capabilities in many applications like vibro-acoustic domains and the domains of aero-acoustics, etc. But when Actran was programmed about 16 years ago, actually Actran was designed specifically to address the challenges 15 years ago in acoustic simulation. And one challenge was to predict, to simulate acoustic transmission through structure. So Actran was actually, the name of Actran was initially the combination of acoustic and transmission. So acoustic plus transmission gives the name of Actran. So just give you a history of the code of Actran. Actran was it's a finite element code. It has fluid volume elements to model air or heavy fluid, and it has the free field radiation condition to model anechoic condition, for example. And in Actran, we can also model structure elements, including lightly damped structure or heavily damped structure, single layer structure or laminated structure, homogeneous material or composite material, and there is also capability in Actran to model detailed elements like the spring elements, rigid body elements, or beam elements that connect different structure panels. And we have the porous material implemented in Actran to simulate the absorbing capability of porous material, and that is based on the belt theory that I will introduce a little later. To characterize the acoustic transmission of a structure, we need to apply excitation on the structure numerically. So in Actran, we have two categories of excitations. One is the deterministic category, including like acoustic monopoles, plane waves, etc. But in order to simulate a more realistic loading condition, then we should use the second category. That is the random excitation, including diffuse sound field or turbulent boundary layer condition, etc. And in Actran, we have the GRI support to set up the model, so that we will see that through the next example. So in this example today, we are going to model acoustic transmission through a building partition, and the profile or the thickness view of this partition is given on this page. We have a plaster material on the left, and followed by a air gap, and then a rock wool absorbing material, and then another air gap and the plaster layer on the other side of the wall. The panel geometry is 3 meter 6 by 2 meter 5. The total thickness is 72 millimeter in width, in thickness. And to model such a problem, we need to model in Actran 3 key ingredients. So first, the modeling of the structure itself, including all these complexities, and the modeling of the airborne excitation, diffuse sound field, and lastly, the modeling of the reception condition. And in this case, we are modeling a anechoic room on the other side. Then we are going to calculate the transmission loss in Actran. So I will follow up the following, do the following part of the presentation in an interactive way with presentation of PPT and manipulation in the Actran software. So first, we are going to create the mesh of the structure. So in Actran, there are basically two ways to handle the mesh. So one way is to import a mesh that is created in an external mesh tool, like Partition, like SimExpert or ANSA, etc. Another way to create a regular shaped mesh is to do that in the graphical user interface of Actran, which is called Actran VI, so that I will share my screen now on this graphical interface in Actran. It integrates a mesh tool called BoxPro. So BoxPro is very suitable to create regular shaped or box-like shaped geometries. So with the BoxPro tool, we first define all the regions that is covered by the different parts involved in the model. So with the along the X, Y, and Z direction, we will define the starting point, the ending point, and a step of graduation. So here we define a series of vertical grids along the X direction, and in the same manner we define these grids along Y direction and Z direction. So on this grid we will define later on different regions for different parts of the model. So I will first, so that the model is already prepared, I will just walk through the different parts and to illustrate the modeling process. So on this layer 0, it is its dimension is 3, so it's a solid element ranging from X from 0 to 3.6, in Y from 0 to 2.5, and Z range Z from 0 to 0.012. So this corresponds to the dimension of the plaster plate. Okay. And then on the plaster plate, we will define this layer of a small layer of air gap, okay, with this very small thickness, and then a thick layer of the porous material, the rock wool material, And then on the other side of the model, we'll have the same thickness for the air gap and the plaster layer. And in the design of this building partition, there are studs here represented by this black line connecting the two plaster panels. So these studs, they are also modeled in Actran using the using the 1D geometry. So 1D is 1D geometries are actually the lines. So we see here the definition of the different lines. Okay, so I will hide this middle layer to show clearly this where these studs are designed. Okay, they connect the two plaster layers. Okay, so that is the mesh of the wall partition. Then, when the mesh is created, we need to create the physical component. So we will use fluid component or fluid element for the air gap. We will create a structure element. So in this case, we will use this solid shell element and the beam element for the structure. But as we can see that in Actran have comprehensive libraries of structure elements to in order to model other types of structure and their connections. And the rock wool, the parts material need to be modeled in this example. In Actran, we base on the BIOT theory or the BIOT model to model the parts material. So BIOT theory is what it does is to describe globally the it describes globally the parts material by several properties. So there are properties related to the skeleton inside the parts material. There are properties related to the fluid inside the parts material, which is air in reality. And there are several properties related to the, let's say, the interaction between the skeleton phase and the fluid phase. For example, we have tortuosities, resistivities, porosities, etc. Now, when we have all this set of properties measured or provided by, let's say, by the provider of your company, for example, then we can use the complete poroelastic model to model the rock wool material. But in some cases, there are missing properties. So, which means all these properties cannot be measured or cannot be provided. Then in Actran, we implement some simplified models like the rigid porous model that assumes perfect rigidity of the skeleton, so the skeleton cannot be compressed, or lumped porous, which assumes a very soft skeleton. And also some empirical models like the Delaney-Besley model or the Mickey model. So all these simplified models, their advantage is they require a limited number of properties while keeping a satisfactory accuracy at given frequency ranges. So so we will see the modeling of the parts material. And about the solution approaches, In Actran, we have both direct frequency response approach or modal frequency response approach. The direct frequency approach is very suitable for in the case where we have a complex and high value of structure damping and porous material. While the modal frequency approach is interesting because it often reduces the computational cost, but it's only suitable for low damping structure and without any porous material included. So let me come back to the Actran VI and walk through the different elements that we just mentioned. So first, we see that we have a direct frequency response here. Now, the reason for that is we have a porous material which cannot be correctly modeled in the modal frequency approach. So we use a direct frequency response instead. And inside, we define a frequency range. So here we start from 20 Hertz, goes up to 500 Hertz, and we simulate a frequency step of 5 Hertz. Okay, and the different layers are assigned to different components. Now, for example, the plaster layer, it goes to a solid shell component, while a solid shell component is a volume element that has a shell bending formulation in the element, and the material related to this solid shell has the Young modulus and the Poisson ratio and solid density. So these parameters of the plaster material. Okay, and then let's take a look at the porous material. Okay. Now, in this case, we are using a rigid porous implementation for the rock wool. We could also use other types like the porous UP, which is the complete poroelastic implementation, or other, as we can see, simplified formulations that are available. Okay. And if I click in the material of porous material, then we see a set of properties that are required. Now, many properties are they have values by default because for fluid properties we simply need the properties of air, which is known, and we see that there's fluid skeleton properties and the elastic properties and micromodal properties. Okay, and for the stud, we are using beam component, okay, with the material having equivalent beam properties. Okay, so that is the modeling of that structure. When the structure model is prepared, then we need to load it by an excitation. In this case, we apply the airborne excitation with the characteristics of a diffuse sound field. So, as I mentioned previously, the diffuse field is produced experimentally by a strong acoustic force excitation in a reverberant chamber. Multiple reflections along the boundary rigid walls give a diffuse field, which means the at any point in the room, as well as on the surface of the tested object, there's no predominant propagation of acoustic waves. Sorry, there's no predominant direction of acoustic wave propagation. Okay. And in nature, diffuse sound field is a random excitation. In Actran, we implement several types of random excitations, like diffuse sound field or the turbulent boundary layer formulation. When we deal with random excitations, we different from deterministic excitation. For random excitation, we work on quadratic terms. So we use the power spectral density representation for the excitation and for the response. A power spectral density, or PSD, correlation, cross-correlation matrix defines the correlation or relationships between excitation at one point on the plate and another point with a given distance to the first point. So a correlation PSD matrix defines the complete correlation relation of the diffuse sound field applied on the structure surface. And each term of this PSD matrix will have this form, which means the correlation of 2 points under a diffuse sound field depends only on the distance between these 2 points and the frequency being analyzed. And the cross-PSD matrix is a dense, it's a full matrix. In the direct frequency response, the applying that matrix directly as excitation is computational cost prohibitive. So we will find other ways to introduce this PSD excitation to the surface. Well, there are several ways existing in Actran, and I will introduce this sampling technique. So the sampling technique consists in downgrading the PSD matrix into linear terms, so from quadratic terms into linear terms. So the steps is in the sampling process is to first decompose the matrix into products of two triangular matrices, and then we take one of them and multiply it by a certain number of random phases, and this certain number is actually the number of realizations, or in other words, the number of deterministic loads that we created. So if we take the and then this sample excitation will be applied on the numerical model to calculate the response. Of course, each response has a deterministic nature, but if we calculate the average results of these realizations, then we will approach to the expected response created by the random excitation, given the number of samples is sufficiently high. So this approach is interesting in terms to reduce the computational cost, and also it is interesting because it offers not only a expected or average value, but also with this method we have access to dispersion indicators, and so we can also analyze from the results the dispersion related to uncertainties, as it can happen also in experiments. So with this theory explained on diffuse sound field, I will show you how to apply that in Actran. Well, the way of applying diffuse sound field is actually quite easy. So in the boundary conditions section, we see among the many types of boundary conditions, there are several types of random excitations, and one of them is the random diffuse sound field. So while it has been already created, I will just go into it. And we see that there's no now let's go back to the idea of modeling the reverberant room in which diffuse sound field is generated. As we see that there's no reverberant room modeled in this example. So in reality, the diffuse sound field is directly applied on the surface of the structure in touch with the reverberant room. So it's applied on the lower surface. And so we define a random diffuse field. And then we specify the number of samples. This is 30 here, and according to our experience, it is sufficient for this type of problem with this type of size. And then we need to define the properties of the medium in touch with the surface, or the medium from which the diffuse sound field comes from. So it is the speed of sound and density of air, simply. So in this way, we define the diffuse sound field. Okay. Now I will come back to the presentation. The last component in this numerical model is the reception condition. In this case, we want to define a anechoic room. In Actran, there are several ways to model the anechoic room, or in other words, to model a free field sound radiation. There are infinite elements. There is infinite element. There is the adaptive perfect mesh layer technology, or APML technology. So for both infinite elements and the APML, a volume mesh will be created. As we can see here in this picture, the volume area is this the area enclosed by this green surface. So air will be created inside, and the free field condition will be created on the exterior surface. And for flat surface, there's a third alternative, which is called the Rayleigh integral method. So the advantage of this Rayleigh integral method is that it doesn't rely on the volume mesh. The acoustic radiation can be done into free field directly on the structure surface. No exterior mesh will be needed. The limitation of Rayleigh surface is that it only applied on flat surface. It cannot be used for a curved surface. So in our case, I will create a infinite element domain with its volume in finite elements. So I will just show you this box pro mesh that has been created for the air volume. and the infinite surface. The infinite surface, they cover the top surface and the four lateral surfaces. Okay, so this is the numerical model, and the computation was launched and completed previously. I will show you the result obtained in this problem. The result we will look at the sound transmission loss indicator, and it can be plotted from the text result in this PLT format by Actran. So basically, we will need a ratio between the incident power and the transmitted power. And to do that, I will, first on the x-axis, I will apply the frequency. Okay. And on the y-axis, I will apply our transmission loss indicator. It takes two terms: the incident power that I will get from the, as you can see, the sample random diffuse field, okay. And the transmitted part will be found in the infinite element domain through which the acoustic radiates. So we get the random power evaluated through the infinite surface. Okay, as I plot, we see this a very typical curve of transmission loss, which is described in dB. So on the left we have the dB, and on the vertically we have the dB values, and then through frequency it changes. So typically at lower frequencies, we are in the very low frequencies, the system is controlled by rigidity of the structure, and then we will have the first modes of the structure that will going to dip in this frequency. And then typically, if the problem has little damping, then we will have quite shaky curves, which is the zone controlled by the structure modes. But as we have some damping in the system, we don't see too much of that phenomena. And then at some moment, as the modal densities increase, we will enter a mass law region where the curve goes up with a constant slope. And then, while in this demo model, we didn't go to higher frequencies, which could be done by finite element modeling. Now, in higher frequencies, we will have some coincidence between the acoustic wavelength and the structure wavelength, and that will bring the curve down at the frequency that is called critical frequency, and then it will goes up. But we will see that behavior in the case studies later on. Now, let's come back to the presentation. So on this page, we see this TL curve that I just plot together with two other TL curves. So our configuration is this one, the TL stud configuration 1. And then there is a configuration of TL without stud design and a configuration with another type of stud. And so the purpose of these three curves is to illustrate how the studs change the behavior of the transmission loss. So typically at lower frequencies, because the increased damping and increased rigidity of the studs, we have the increase of TL and the shift to the higher frequency ranges. And at higher frequencies, because the studs, they are connecting the two plasters, so they reduce the efficiency of the parts material in terms of separating the plasters. So consequently, the vibration of the transmitted part of the plaster will be amplified because of that connection, and that will bring down the transmission loss, as we can see here at this higher frequency region. So this is the example that we walked through on this typical wall partition problem. And now I will show you, to finish this webinar, I will show you 3 other case studies. So first one is the transmission loss example of a car window. Now the final product of a car, well, this is a windshield, of the car windshield is composed with multiple layers. So we see here a glass layer, a PVB layer, and another glass layer in the ceramic frame. And we see that apart from now on this sketch, the energy distribution. So we see incident energies, reflected energies, and some energy is absorbed or damped by this PVB layer inside the windshield, and the part is transmitted. So on this page, we see the result of a single layer. To start the measurement, we started with a single layer glass, and to see how the thickness of that glass will change the transmission loss. Now, designing this type of glass is always a balance between the transmission loss and the thickness. The thickness means weight of the product. So in this measurement, following the ISO 140 standard, we have a reverberant room, a anechoic room for reception, and this layer of glass in between. The dots result are the experiment, and the line curve result are the Actran simulation. And we see for both thickness 3.1 millimeter and 2.3 millimeter, we have quite good correlation between both results. And we can observe that a shift in frequency and an increase in the TL that is made by different thickness values used. So this is typically the critical frequency that I mentioned in the TL curve. And the next example is about the sealing effect on the transmission loss. Now, seals are a critical part in window design, especially in the automotive window. Now we are looking at the glass run channel design. Now, there are actually 2 phenomena that happens on the sealing. So first, the seal is itself a conductor of acoustic waves. So there is acoustic sound transmission through the seal. So that is important. And another role of the sealing is that the seal design will impose a boundary condition on the window. Okay, so that is the object of this study, to evaluate the sealing design that changes the transmission loss through the window. Okay, so we see similar setup for measuring the transmission loss, and typical curve on the transmission loss. So to run this project, we have gone 2 steps. In the first step, the MARC software, which is a nonlinear software, finite element modeling, was used to simulate the seal and to calculate the position of the sealing and the glass. And then a second step we used Actran to model the acoustic transmission through the window while taking the ceiling design into account. So we see results obtained with two ceiling designs. So on the left we have 2 lift ceiling, and on the right we have the 3 lift design. We see there are some difference between these two designs, and this difference will bring a significant change in this TL curve of the window. Okay, so the last example is a wind noise into transmission into a cabin. Now, here we are not using a diffuse sound field, but we are modeling a realistic wind noise that is transmitted into a simplified car cabin. To simulate the wind noise created by the A-pillar of a car, first their CFD code was used to calculate the turbulent wall pressure on the structure, so in particular on the windows and on the windshield of this simplified cabin. And then in the Actran model, we modeled the glass, so the structure which is in aluminum, the seal, the acoustic treatment that is available in this cabin. So there are, as you can see in the detail, there are foam layers, there are heavy damping layers, and this skin layer which is aluminum. And the inner cavity is also modeled in Actran. And then the CFD result is of the turbulent wall pressure is mapped on the Actran mesh, and then Actran will read that excitation and calculate the sound transmission through this multi-layer structure and get the result at the inner microphone position. So we can see that we got relatively good correlation between the simulation and measurement on now one of these microphone positions. So the measurement was done for 2 different wind speed, one at 110 km per hour and another at 130 km per hour, with 2 flow directions, one at 0 degree and one at 10 degree. And for both cases, we obtained a relatively good correlation. So this is the last case of my presentation. Now to conclude, we have seen that Actran can be used to simulate acoustic transmission, or in other words, acoustic insulation through structures. So both direct frequency response and modal frequency response are available for different purposes. Modal frequency response is suitable for lightly damped structure, and direct frequency response is more suitable for highly damped, complex damping and porous material. So if we use direct frequency response, we can model the complete structure in Actran using its comprehensive structure element library. Anechoic conditions or any cavity conditions on the reception side are also available in Actran. And random diffuse sound field or turbulent wall pressure can be applied in Actran to model realistic loading conditions. So that was the presentation, and with that, I would like to thank you for attending this webinar, and let's go through the Q&A session.